Welcome. Today I'm going to be going through an implementation on Sonic Pi of Todd Barton's Krell music. Now, Krell music is Todd Barton's implementation of BB and Louis Barron's soundtrack for The Forbidden Planet. And it's the music of the ancient race that had died out. So it's basically influenced by the film, and Barton essentially tried to recreate something along those kinds of lines using his Buchla modular synth. Likewise, it's now become a kind of a standard kind of thing in modular synthesis to sort of work on kind of Krell patches. So obviously, once I sort of started working in Sonic Pi and sort of kind of got used to it, still am getting used to it, I thought I would implement something like this. The advantage of using a modular synth is that you can take an envelope and you can share that envelope across a number of modules and adjust a variety of parameters. You can also invert the envelope. You can also scale the envelope. You can also adjust it in terms of attenuation and so on. So there are a lot of things that you can do in a module or in a modular system. It's actually quite difficult to sort of implement in, say, a live coding environment like Sonic Pi. This isn't in any way to sort of do Sonic Pi down. It's quite amazing in terms of what it does do. It's just that sometimes I would like to be able to have a single resource that I can then farm out to a number of processes. So this is basically a self-generating patch. Envelopes in modular synths, if you have the right kinds of modules, will also generate a pulse at the end of a cycle, or at the end of a particular stage of a cycle on an envelope. So if you have the end of attack, or the end of release, the end of decay, you can then have a pulse that then can be used to then to kickstart a new process that then might actually be feeding back into the same sound and modulating that as well. So those sorts of things aside, this is kind of my implementation of Krell music. I've actually got like 4 or 5 different versions of this. I've got some that are quite involved. I'm not sure it's the best code in the world. I'm not really a coder, but where the dynamics, i.e. the amplitude, is shaped by the pitch of the note. So the higher the note goes, the more that the amplitude is kind of brought down. It's kind of a bit like filtering. Whereas, when the note is much lower, the amplitude tends to be wider or louder, higher, whatever. So the filter would be more open. And this is really just kind of a dynamic shaping thing, because once you've sort of gone 5 or 6 octaves above, that note can be quite shrill. So that's kind of the idea behind that. Let's have another quick listen and then I'll go through the code. For this patch, I've got 2 variables. One is sleep vowels, which is here, and the other one is N choice. N stands for note. So sleep vowels is essentially a ring of sleep values, as its name suggests. And those sleep values are used to determine the duration of the note. So these are selected. We can see them down here, and I'll go through that in a second. And then these are also used to calculate attack times and release times as well, to shape the envelope of the sound in terms of its timbre. And these values, 1.0 can be assumed to be something like, it's 1 second at 60 BPM. Let's say it's a quarter note. So values to the left are kind of equivalents of, so 0.75 in my understanding is like a dotted eighth note or 3/16 notes. 0.5 is an eighth note, 0.25 is a 16th note, and so on. And then the ones to the left of 0.25 are dividing by 2. We have values that essentially go, first of all, we have the intermediate value of 1.125, which is half the value of 0.25 here. And then it just basically goes off to the right. So you could create you can extend this by having ever longer kind of values. You can have 8.0, 12.0, 56.0, and so on, right? Or any variations thereof. The second one for end choice is that basically I use a scale here. Now this scale is chromatic, but because it's going across 5 octaves, which is here, the nature of the Krell music isn't one that has that is kind of linear. So it's not like a scale where it's going sort of scale degree 1, 2, 3, 4, or little kinds of tropes like that. You know, you don't hear do, re, mi. It might occur within the general kind of randomization, but it's not necessarily a specific output. So with it being displaced and randomized across 5 octaves, almost every scale you use will sort of become less familiar. Here's one for a minor pentatonic. Let's have a listen to that. Not too dissimilar, right? So if we constrain the number of octaves, let's say the number of octaves is 1, and let's raise the base of the scale up to C3, we should be able to hear the character of the minor pentatonic now. So this is Lydian. So the choice of scale, which, you know, in terms of a modular synth system, you know, this is the equivalent of kind of using a scale quantizer. At least that's the way I see it. So that's kind of what we have there. So I've returned it to C2 as the base point for the scale, Lydian as the scale type, and the number of octaves as 5. We're going to come back to the effects in a minute, but first of all, I'm going to just code these out. So this is it as a dry sort of sound. So we've got that. Really, there are sort of 2 blocks of code, really. One is to do with branching logic, which is this section here. So if you've ever used a module like Mutable Instruments Branches or Marbles, where you have a branching logic of either A or B as the output of the coin toss, this is basically what that is. So for, you know, if we say 1 in 2 times, so that's 50-50, right? 50% of the time, if it throws tails, get the value from sleep values. .choose means just randomly pick one and put it in the variable sleepy time. Otherwise, if it's the tails, I have a fixed set of values, which are 0.125, which is like a 30-second note, and 0.25, which is a 16th. And that goes in the variable sleepy time. So for 50% of the time, 50-50, it's either take it from the sleep vowels or take it from the fixed one, which is here. And that fixed one can be anything. But what I'm trying to do here is to at least sort of try and enforce a kind of a shape on it. You don't want absolutely random values, but you do sort of need something that feels like it kind of shapes it. So let's have a listen to just the fixed ring, which is this one here. So as we can hear, that doesn't really have much in the way of variation. It's just pretty much, you know, there are only two values and they just cycle between them, selecting randomly between them. And it doesn't feel like there's much in the way of, you know, difference. Whereas here, let's listen to it when it's the randomly selecting from sleep values. So that one in turn might feel a little bit too random. Now, when I do things like a Krell patch on the Modular Synth, what I tend to do, sorry, I'm trying to make sure I take out all the right bits of code so that I don't crash. I'm hoping to get through this video without actually crashing, which would be really good. You know, if I was using make noise maths as the envelope generator, the cycler that will also give me the sort of the clock kind of pulse output and so on, then I would be varying that manually. So I kind of think of this lower sleepy time as a kind of that sort of thing. You know, it's not really human, as it were. It's not a human being turning a knob, but it's something like it. That's kind of how I've thought about that. Now, one of the other things that we can try is change the number of coin toss or coin tosses. So let's say we put it to 5. So 1 in 5, it will pick a value from sleepy time, and then for the rest of the time, it will pick it from the fixed ring. So let's have a listen to that. So you can hear where we have those long values coming in. Those are the points in the branching logic when it takes the value from sleep vals. So that's something that we can do there. We can also change which is heads and which is tails, right? So we can make the fixed ring heads, and the one from the variable list, we can make it tails. It's 50-50. But if we change that to 1 in 3, so here we go. So we get less, you know, we only, for 1/3 of the time, we get access to we access the fixed ring. So you could change this to anything, you know, 13. And each sort of small sort of change gives us something different to kind of, you know, as an output. These sorts of things will be quite difficult to implement in, you know, by changing one value and then it has an overall effect on the whole piece. It's quite difficult to do in a DAW, really, especially if we've got kind of fixed kind of MIDI clips and things like that. Really difficult to just change one thing and affect the whole output. So it's one of the reasons why I sort of like using like something like Sonic Pi as well, because it gives me a different way, different kind of window into doing things, right? So that's what we have there. So let's have a look at the basically the two commands. This one is basically dealing with playing the note, end choice. So end choice takes us back up here to the scales. And what I have is that the variable sleepy time, which is basically the sleep time, sorry, variable naming, is divided by 2 for the attack and divided by 2 for the release. So when you put the two together, you add them together, you have the total sleep time. So the sound characteristics of the instrument should decay naturally, as it were, right? It should feel like a kind of the envelope is being applied as it sort of fades out. And then the last thing we have is the panning. So the panning here is basically random distribution. So I've got it at minus 0.45, which means that it should start roughly about 45 degrees or thereabouts on the left-hand side, and then it bounces between left and right across this kind of stereo spread. At least that's my understanding of it. Let's have a look at the effects. So we're going to look at the reverb first of all. Let's have a listen. Now the size of the reverb room is really interesting. So let's try 0.1. Quite dry. This is 6. Okay. Now with the effects, we're going to have a look at those. So I'm using random values here with the effects. This is rand is range random, so it's a range of random values between here for the phase 0.125 and 0.25. So you're asking the code or the Sonic Pi to essentially select a value randomly somewhere between there. Likewise, the decay of the echo is between 0.7 and 2.5, and then finally the mix, a little bit more complex because of its nesting of another range random here, but the mix can go from 0, which is dry, right the way through to any value between 0.25 and 0.45. So we never really quite get to a 50-50 wet-dry mix. Let's have a listen with the echo. Okay, so as I've said, this is a kind of a basic implementation I've done, a very rudimentary one, as it says in my comments at the top there. If you like the code, it's available on my GitHub. There's a link in the description below. I've got other code that's on there as well, which you might want to download or play around with. I'll be going through some of the other implementations as well, so I hope you've enjoyed this. Thank you for spending some time sort of listening to this and kind of thinking about how we might go around solving a problem that is achievable, say, in a modular synth, but less easy or less straightforward in other systems. But again, by doing this, we kind of challenge ourselves to try and understand what are the really good aspects of the work that we do and what things are also transferable. Some things we can do with more ease, and others just kind of we have to adapt, right? And that's all that this really is. So anyway, thank you very much for watching. I hope you've enjoyed it, and please remember to like and subscribe, and see you next time. Bye for now.